Hello, everybody. My name is Puneet, and today we're going to do a unit operations question on creating an xyT plot for a binary mixture. I'm going to start sharing my screen and we're going to jump right into this question. And then, so this is kind of like the question where we're given the binary mixture of chloroform and dichloromethane. This is the data for ABC for the Antoine's equation. We will be using that to figure out the pressures as well as how temperature will relate to them. And uh, essentially, the idea is the pressure remains constant at 1 bar, which is approximately equal to 750.056 millimeters mercury. And what I am hoping for is an xyT plot. So at the end, I'm looking for a plot with mole fraction of one of the components, let's say chloroform, on our x-axis. And then on the y-axis, we're hoping to have different values of T. Considering I am taking my component 1 to be chloroform, so let's just say chloroform is my component 1 and dichloromethane is the component 2. So this is x1, this is x2. And we are hoping to find the liquid component as well as y, the vapor component, so that we can get a plot that will look somewhat like this, where this area is the liquid vapor equilibrium area. So we have nothing to really start with except that there is a pressure of 1 bar that's consistent. And then the only other thing that we know is the ABC values. If these are not given to you, you can search them up or refer to any unit operations handbook and you'll see these values over there. To plot a plot such as this is the xyT, x or y actually, diagram, you need, I'm hoping to end up with a data table that sort of gives me T values at different mole ratios of mole fractions of, let's say 0, 0.2, 0.4, 0.6, 8, 1, so on and so forth. So that's kind of like the idea. I do want to end up having something like this. And once I've figured this out, probably have the y1 values associated with it as well. So, I can end up having two of these lines in terms of this plot and then that plot. So that is the goal for me to make this xyT diagram. Now the question is, how do we figure out what temperature to use? What we do know is the pressure, the constant pressure, which is this. The equations that we will be working with while we're solving this is the Antoine's equation, which says log of P. I'm going to use log 10 P formula. And like I said, A, B, and C values are right here. Now, what is this P? This P comes from this equation where P is made up of the partial pressures from the component 1 and the component 2. This is the mole fraction times the pressure of the pure component at a given temperature, which is actually really crucial because these values will be found at a particular temperature. The thing here is that we have this pressure over here. We know what is the pressure value. But what we don't know is the temperature. So if you can understand what's going to happen here is we're going to have to think and guess what temperature values we can use at different mole ratios, like over here, such that we get P1 and P2, the pressure of pure components, that will satisfy this equation. Now, let me show you what happens at x1 being 0. This is an easy situation because when x1 becomes 0 and I put 0 over here, what's going to happen is this whole thing is going to become 0. And because x1 is 0, we're only going to be left with uh, P2 sat T, which means the pressure is actually just P2 sat T, which I can easily find, the temperature I can easily find by using Antoine's equation over here. So because I know the p-value is 750.056 millimeters Hg, I can simply use this as the p-value in the Antoine's equation. So this will go as p-value in this equation. I do have the A, B, and C values for, remember this is P2, my component 2 is dichloromethane. Chloroform is my component 1. So I'll be using the A, B, and C values for this component, and I will be able to find this. So what I'm going to do here is plug in all the values here. So log with the base 10 of P equals the A value. Sorry for the back and forth. Maybe I'll just write the equation over here. The A value minus the B value over T plus the C value. And we're going to just, I want to move this down here. So this becomes a really easy equation for us to solve because there's only one unknown. And the temperature that I got here was about, I guess, 39.8 degrees Celsius, close to that. And that's easy for us to figure out because there was just one unknown. Now imagine what happens when we try to explore something like when the mole fraction becomes, let's say, 0.2. Now we know the pressure, I'm going to just rewrite the equation for us. Add a T and then this at T. So we know that the pressure value is still 750.056. That's going to stay constant throughout these runs. However, now we're facing this problem where, just put x1 as 0.2, so this will be 0.8. We have one equation and two unknowns. So one thing we can do is just try guess and check. But you see the guess and check method is going to be pretty hard because it's not just you're assuming different values of P1 and P2, you're assuming different values of T such that when you put it into Antoine's equation, the pressure, the P1 and P2 comes out to be such values that the pressure overall comes out to be 750. But here's a faster way to do this. We can quickly use Excel solver to do this really quickly for us. So I'm going to show you how to do this on Excel with a solver. So I over here I have the setup over here. I have the x1 values, which which are just something that I'm exploring and hoping to have on the graph. Now P1. I am trying to find P1 sat. The formula for P1 sat is the Antoine's equation. So here, the formula is just going to be anti-log of the A value. I'm actually just going to put the numbers, or let's just put this. This is going to stay consistent for all, so we can use the dollar signs. The A value, and then we have minus the B value divided by T, which is something that we're going to have here, plus the C value over here, which I'm also going to. The dollar signs, what they do is, as I will drag the Excel formula down for all the other X values, the ones with these dollar signs will stay consistent, which means if I were to now drag this down over here, so if I explore this formula over here, you see the A, B, and C values here are still the same, but the T value would be the corresponding T from this location E11. And that's because we want to make sure that these values don't change, but when we drag down, the temperature should be, different for different X values. And similarly, P2, when we write the equation for this, is going to be exactly the anti-log of the A value, but here it's the second component is dichloromethane. So we're using the dichloromethane minus the B value over here divided by T. Okay, plus C. I need to select T. Hold on. Let's go back here and put T. Alrighty, I think this is good. And once I have established, I can drag it down for the others. Mind you that right now the values are this because T value is nothing, it's 0. So it's just really computing our P1 and P2 sats based on the T value. Okay, if this is clear with the Antoine's equation, we know that the pressure value here should be 750. So I'm going to just put a random column cell here with the pressure value that this is our target pressure value is this. So, but I guess, the formula for P is going to be, X1 times P1 sat plus 1 minus X1 times P2 sat. This. And the goal is that this P should be equal to the target P. Okay, so I'm just going to drag this down. This is going to be, if we look at the formula, it's X1 times P1 and then 1 minus X1 times P2. So the formulas are all good. Now here is where we're going to use solver because we want to select T in a way that makes our p-value equal to this. So what we need is to go to solver. I think this one. I wasn't really sure. So solver is not really available in Excel. What you need to do is go to add-ins over here and you basically just search for solver and you want to select this solver free. I'm pretty sure I think these are fine as well, but you want to select the one that optimizes your values or something. I selected this. I also installed this, which actually didn't work as I wanted it to, so it's probably something else. But you want to install, quickly add in solver to your Excel. And then we click on solver, and it kind of lets you do this. So this is the objective. So this is the cell that we want to optimize. So the cell that I do want to optimize is this cell, right? And I want to make sure that this cell has a value of 750.056, which is our target P. So I want this P to be equal to that. So that's our objective. And then the variable that we are going to, um, I guess, change, because everything, if you really think about it, everything just depends on T. That's how we have set up all the formulas. So if T changes, so will P1 and P2. And if those changes, so will P. So E, so T is the variable that I'm trying to um, change. I'm not going to put any constraints because there's nothing that I really want to um, put, but maybe if you want to, like if you want to do that, you could like say that, maybe these two cells should be greater than or equal to 0. Like it's you can put these constraints, but I don't think you need to. I'm just letting you know like there are different functionalities. Anyway, and then we just click on solve. So it's going to solve, and this did not work. Hold on. Objective is set this equal to this. Okay. Variable is this. Maybe the constraints. Let me just delete the constraints. Okay. And let's solve it again. Oh, there we go. Okay, that worked. So I don't know what happened there. But if you look at this t that we got using Excel, and if you compare it to the t that we got while solving this equation at x equals 0, it's pretty similar. I got 39.8 and this is 39.8234. And if you see, this is the value of p we're getting. Similarly, you can run and notice how P1 and P2 have changed depending on the T. So we'll be able to get a pretty good graph such as this. I actually already did it on sheet 1, and these are the values that we're going to get if you continue doing this. And now that we have this, we can actually plot a table. So I'm going to take the x1 values. I'm going to take the t values, and we will try to insert a plot. Let me just, whoops. We're going to insert a plot. Okay, that looks like this. This is exactly what we were kind of expecting. You can actually format your axis so that the maximum is just at 1. So you have something like that. And this is just the x portion of it. We can find the y portion. So y1. The formula to find y1 actually. So once you have found your x's, the formula to find y1 is just your x1 p1 sat over p. In this case, this is going to be the 750.056 that is constant throughout these runs. And p1 sat is what we're seeing at different x values over here in Excel. So we can actually just use this formula. So this is going to be x1, so we can just use this. Hold on a second. Oops. Goals, I'm going to use x1 from here times p1 sat from here, and then divide that by this target p. And the target p is one that I want to actually not move at all. This makes sense because x1 is 0, so y1 is 0, and then we just drag this down. And so those are the values. So what I'll do is I will select that. I will add another series here. So the x values are actually going to be these now. And the y values are just going to be these. And if you do that, you get this, another set. This is kind of what we were expecting. And then you can just label your chart or whatever. In this case, This is going to be your temperature in degrees Celsius, and this is the mole fractions, x, y. And these are the different temperatures, so starting at 39 and then all the way to 60. This portion over here is your liquid vapor equilibrium. Over here, you will see vapor phase, which makes sense because the y values gave us this orange line, and this is the x value, so this is liquid phase. The idea here is because when you heat things up, when you increase the temperature, the molecules have a lot of kinetic energy, so they're moving really fast and away from each other. So at higher temperatures, liquids and mixtures are more likely to exist as vapors. However, if you had done a PXY diagram for the same thing, you would have expected a graph looking like this, with actually you would be expecting the graph looking like this. So this, our bubble line, is actually going to be a linear line. But in the XYP, your liquid will be at the top and your vapor will be at the bottom, which is opposite to that of the TXY diagram. The reason for that is as you increase the pressure, you're actually pushing those atoms and molecules of gas closer together and compressing them vapors into liquids into liquid. So this is the kind of plot you will be expecting if you did an XYP diagram. But the main reason for this video was to show you how you can use Excel solver to quickly solve for the or instead of doing guess and check, you can quickly just input all the values and data in here and then get your temperatures. What I will be doing is putting maybe a link to Excel or Sheet somehow with these um, formulas built in. So when you watch the video and you know what you're doing, you can just simply click on the Sheets video link and then get access to these values, to this Excel sheet with the pre-built formulas for you to use. All right, that's all for today. Hope you enjoyed and this was helpful. Have a great one. Bye bye.